This text lists the necessary libraries for data manipulation, visualization, machine learning, and progress tracking. 1. NumPy – library for numerical operations in Python. 2. Pandas – library for data manipulation and analysis. 3. Matplotlib – pyplot – library for creating data visualizations. 4. Random – library for generating pseudo-random numbers. 5. Collections – Deck – a deck, double-ended queue, is a data structure that allows you to insert and remove elements from either end. 6. Swise – provides functions and variables to manipulate different parts of the Python runtime environment. 7. Math – provides mathematical functions defined by the C standard. 8. Keras – high-level neural networks API running on top of TensorFlow or Theno. 9. Keras – models – load_model – function to load a pre-trained Keras model. 10. TQDM – TQDM_notebook – a fast, extensible progress bar for loops and iterable objects in Jupyter notebooks. Importing these libraries is essential for tasks such as handling data, visualizing data, implementing neural networks, tracking progress in loops, and more. They provide a wide range of functions and classes that can make coding tasks more efficient and easier to implement. To configure TensorFlow to dynamically allocate GPU memory when needed and avoid memory fragmentation, follow these steps. 1. Import TensorFlow along with necessary modules like models, layers, and optimizers. 2. List all available physical GPU devices and iterate over each device. 3. For each GPU device found, set the memory growth configuration to true. Enabling memory growth in TensorFlow allows memory to be allocated on the GPU as needed, rather than all at once. This helps prevent memory fragmentation and ensures efficient usage of GPU memory. Utilizing this configuration is advantageous when working with TensorFlow on GPUs, as it optimizes memory usage, enhances performance, and mitigates potential memory allocation problems. This text describes two main functionalities for working with Google Colab. 1. Mounting Google Drive. By using the Drive mount function, you can mount Google Drive into the Colab virtual machine. This enables direct access to files stored in Google Drive, allowing you to read from and write to files within your drive. 2. Changing directory. The code snippet also uses OS/CHDIR to change the current working directory to a specific path in Google Drive, such as Content, Drive, MyDrive, Central Supalik, Deep Learning Finance, TD7, TP7_Q_Trader, Q_Trader. This is helpful when you need to access files located in a specific directory within your drive. These functionalities are essential when working with files or scripts stored in Google Drive within a Google Colab notebook. By mounting your drive and changing the working directory to the desired location, you ensure easy access and manipulation of the required files for your analysis or project. This text describes how to read financial data from a CSV file named *GSPC_2011.csv. The Pandas library and its read_CSV function are used to create a data frame from the data. The index_call equals 0 parameter indicates that the first column of the CSV file will be used as the index column in the data frame. Loading data from an external file like *GSPC_2011.csv is essential for data analysis in Python. The data frame created from the CSV file allows for various data analysis tasks such as cleaning, transforming, and analyzing the data. This script utilizes the Matplotlib library to generate a line plot illustrating the adjusted closing prices of a stock, GSPC, over a specified timeframe. Here's a breakdown of its functionality. 1. Setting the figure size to 15 units in width and 5 units in height using PLT. Fig size equals 15, 5. 2. Creating the line plot with PLT. Plot, NP. Arrange, 0, data. Shape, 0, 1. Data, AG close, label equals GSPC. This plots the AG close prices from the data frame against values ranging from 0 to the dataframe's row count. It also assigns the label GSPC to the data series. 3. Assigning the y-axis label as prices with PLT, y-label prices. 4. Defining the plot title as GSPC prices using PLT, title GSPC prices. 5. Adding grid lines to the plot for clarity with PLT, grid. Overall, this script is designed to visually represent the adjusted closing prices of the stock, GSPC, through Matplotlib. By creating such a visualization, users can effectively analyze and interpret stock price trends, aiding in making informed investment decisions and gaining insights into the stock's historical performance. The agent class represents a reinforcement learning agent capable of interacting with an environment, making decisions, actions, and learning through experience replay. The __init__ function initializes the agent object with parameters such as state size and model name. If the agent is in evaluation mode, as _eval equals true, a pre-trained model is loaded. Otherwise, a new neural network model is created using the _model method. The _model method defines a neural network model using keras with input layer, hidden layers, ReLU activation, and output layer, linear activation. The model is compiled with mean-squared error loss and atom optimizer. The ACT method determines the action based on a given state. It chooses a random action, exploration, with probability epsilon or exploits known information by selecting the action maximizing expected reward from the model prediction. The XP replay method implements experience replay, storing agents' experiences in a memory buffer and randomly sampling a mini-batch for training the neural network model with updated rewards. Utilizing this code enables the creation of a reinforcement learning agent that learns from past experiences, enhances decision-making abilities, and improves performance. Neural networks and experience replay allow the agent to generalize learnings and make more informed decisions. This text discusses functions related to processing stock market data. 1. Format price, n, takes a number n and returns a formatted string representing a price with 2 decimal places. It adds a $sign for positive or zero numbers and a $sign for negative numbers. 2. Get stock data vec, key, reads a stock market data file named key.csv, extracts the adjusted closing prices, and returns them as a list. 3. Sigmoid, x, calculates the sigmoid function of a given input value x, commonly used in machine learning for introducing non-linearity into models. 4. Get state, data, t, n, constructs a state vector based on stock market data, a time index t, and a parameter n. It selects a range of historical data points to create a block, calculates the sigmoid function of the price differences between adjacent data points in the block, and returns the values as a NumPy array. These functions are utilized for pre-processing and transforming stock market data to analyze or train models. The getState function appears to prepare input data for machine learning by encoding historical price movements effectively. Other functions like formatPrice and getStockData vec assist in the necessary data processing and formatting tasks for financial data analysis. The function Q_fit implements a Q-learning algorithm for stock trading. Its main steps are: 1. Initialize an agent with a specified window size. 2. Get stock price data for a chosen stock. 3. Execute a loop for a set number of episodes. A. Navigate through stock price data at each time step. B. Agent determines whether to buy, sell, or hold the stock based on state and epsilon greedy strategy. C. Update agents' inventory and calculate rewards from buying and selling actions. D. Save experiences, state, action, reward, next_state, done, in the agent's memory buffer. E. Periodically replay experiences from memory to update the Q network. F. Optionally save the agent's model every 10 episodes. The Q-Learning algorithm teaches a model to decide when to buy or sell stocks for profit maximization. This approach enables the agent to learn the best policy for trading by approximating future rewards for each action in a state. The function parameters include stock name, window size, batch size, and the number of training episodes. Its objective is to enhance the agent's trading strategy and assess its effectiveness. In essence, this code trains a Q-learning agent to make sequential trading choices based on historical stock data. This text describes the initialization of various variables for a program related to stock market analysis, reinforcement learning, or a machine learning model. Here's a summary of each variable. Stock_name is assigned to the stock name _GSPC _2011. Window_size is assigned an integer value of 10. Episode_count is assigned an integer value of 50. Batch_size is assigned a value of 32. These variables likely represent different aspects of the program, such as the stock being analyzed, analysis timeframe, training iterations, and batch size for neural network training or data processing efficiency. Assigning these values to variables allows for easy modification and reuse throughout the program, making it simpler to adjust these parameters without extensive code changes. This script invokes a function called Q_fit with the parameters stock_name, window_size, batch_size, and episode_count. The outcome of Q_fit is stored in a variable named total_profits. Q_fit is likely a function related to a machine learning algorithm, particularly within the realm of reinforcement learning. It presumably involves training a model, such as a Q-learning algorithm, to understand the optimal trading strategy in the stock market using historical stock data. The function may require inputs like the stock name, window size, indicating the historical context for decision making, batch size, for model training, and episode count, representing the training iterations or episodes. The main goal of this code is to train a model for stock trading decisions, possibly to enhance profitability. Implementing such a script would be beneficial for developing trading strategies that can autonomously analyze historical data and make informed decisions based on learned patterns. This process uses the matplotlib library to generate a plot illustrating the progression of total profits over numerous episodes. Here's how it achieves this. 1. Adjusts the plot size by setting the figure size to 15 by 5 inches. 2. Plots the total profits data with episode numbers on the x-axis and profits on the y-axis. 3. Includes a horizontal line representing the mean value of the total profits data. 4. Labels the x-axis as episodes and the y-axis as gains for clarity. 5. Titles the plot as evolution des gains en fonction des episodes, meaning evolution of gains based on episodes. 6. Adds a grid to the plot to enhance the visibility of data points. Utilizing this code is vital for visualizing profit trends and fluctuations throughout various episodes, aiding viewers in understanding and analyzing the information. Presenting data visually allows for better insights, pattern recognition, and informed decision-making. This function, getStockDataVec, reads stock data from a CSV file in a specified directory based on a provided key. It then calculates the logarithm of high, open, low, open, and close, open values from the stock data and stores these values in a dictionary. The function processes the stock data to create a pandas data frame with columns for close, high, open, low, open, and close, open ratios. This formatted data is beneficial for financial analysis and modeling purposes. This code is essential for restructuring raw stock data into a more organized format that includes derived features needed for further analysis or predictive modeling. It extracts relevant information and transforms it into a usable form, preparing the stock data for analysis. The function getState takes three parameters: data, t, and n. It computes a state vector by applying the sigmoid function to price differences at various time steps within a sliding window of size n over the data. The window starts at time t and goes back to tn, inclusive, for each column of the data array. The sigmoid function is used to introduce non-linearity in machine learning and neural networks. It scales input values to a range between 0 and 1, typically for tasks like binary classification. This function likely preprocesses data or derives features for a machine learning model, particularly in time series data analysis or sequential modeling contexts where capturing sequential patterns is crucial. The function QFIT is defined to train an agent using reinforcement learning for making buy and sell decisions in the stock market. Here is an overview of the functionality. 1. Initializes an agent with a state size determined by the window size. 2. Retrieves stock data for a specified stock. 3. Configures parameters like batch size, epsilon decay rate, and initializes a list for storing total profits. 4. Executes a loop for a specified number of training episodes. 5. For each episode, initializes the state and variables, and loops over each time step in the stock data. 6. At each time step, the agent takes an action, buy, sell, or hold, based on the current state, using an epsilon greedy strategy. 7. Receives a reward based on the action taken and updates the agent's memory with the experience tuple, state, action, reward, next_state, done. 8. Conducts experience replay when a certain number of experiences are accumulated to learn from past experiences. 9. Repeats the process until the end of the episode. 10. Calculates and handles the total profit for the episode based on certain conditions. 11. Periodically saves the model during training. 12. Returns a list of total profits obtained in each episode. This code applies reinforcement learning to train the agent on historical stock price data in order to optimize cumulative rewards, profits, over multiple training episodes. Experience replay is utilized to enhance the agent's decision-making abilities over time by learning from previous experiences. This script unpacks a tuple into three separate variables: stock_name, window_size, and episode_count. The tuple is GSPC_2011 feet, 10, 50. Each variable is then assigned a value from the tuple. Stock_name receives GSPC_2011 feet, window_size is set to 10, and episode_count is assigned 50. This code simplifies the process of setting multiple variables at once from a tuple or list, enhancing code readability and conciseness. In this instance, it initializes variables for stock name, window size, and episode count for potential use in subsequent calculations or processing. The script seems to be invoking a function QFIT with the arguments stock_name, window_size, batch_size, and episode_count. It aims to utilize the QFIT function to compute total profits using the given parameters, such as stock_name, window_size, batch_size, and episode_count. While the detailed workings of the QFIT function are not visible, it seems to be connected to a Q-Learning algorithm for stock trading or financial analysis based on the function name and the provided arguments. In general, this script is likely intended for training a Q-Learning model on stock data to forecast and potentially optimize profits according to the specified parameters. This snippet generates a line plot of total profits data points on a graph using the matplotlib library in Python. Here is an explanation of what each part of the code does. 1. Setting the figure size to 15 units in width and 5 units in height where the plot will be displayed. 2. Plotting the total profits data points on the graph with their index positions along the x-axis. 3. Adding a horizontal line representing the mean of total profits values across the entire plot to visualize the average profit value. 4. Setting the x-axis label as episodes. 5. Setting the y-axis label as gains. 6. Setting the plot title as evolution des gains en fonction des episodes. 7. adding a grid to the plot for improved readability. This code helps visualize the changes in profits across different episodes effectively, aiding in the identification of trends or patterns in the profit data. The function named QFIT implements a Q-Learning algorithm for stock trading. Here's an overview of how it works. 1. Initialize an agent with a state size determined by the window size and set up necessary variables. 2. Obtain stock price data for a specified stock. 3. Iterate through a defined number of episodes. 4. For each episode, a. Set the initial state using stock price data and window size. b. Begin with zero total profit and an empty stock inventory. c. At each time step, agent selects an action, buy, sell, or hold, based on its Q-value policy. Update the state using new stock price data. Adjust the reward and total profit according to the action taken. Update the agent's inventory based on the action. Store the experience tuple, state, action, reward, next_state, done, for learning. Implement experience replay when needed to enhance the agent's Q values. d. At the end of each episode, close any open positions in the inventory. Display the total profit for the episode. Save the total profit for analysis and plotting. Save the model to a file every 10 episodes. 5. Return a list of total profits obtained in each episode. The Q-Learning algorithm in this function learns a policy for trading stocks based on the specified state representation and reward mechanism. Using deep reinforcement learning for stock trading enables making more informed and potentially profitable trading decisions by leveraging historical stock price data. This snippet sets up variables for a stock name, window size, and episode count. It then calls the QFIT function with these parameters. The explanation of the code is as follows. 1. Stock_name. It holds the name of the stock data for analysis, GSPC_2011. 2. Window_size. It represents the size of the analysis window, set to 10. 3. Episode_count. It indicates the number of episodes or iterations in the analysis, set to 50. The QFIT function is invoked with the stock_name, window_size, batch_size, and episode_count as arguments. This function appears to be used for analysis or model fitting with stock data. Essentially, this code sets parameters for a stock analysis using the QFIT function, enabling customization of the stock name, window size, and episode count to conduct flexible analysis on stock data. This segment utilizes matplotlib to create a visualization representing the evolution of total profits over a series of episodes. Here is a breakdown of the steps performed by the code. 1. Create a new figure with a size of 15 by 5 inches to display the plot. 2. Plot the data points, total_profits, to show the trend of profits over the episodes. 3. Add a horizontal line indicating the mean of total profits across all episodes. 4. Set the x-axis label to episodes. 5. Set the y-axis label to gains. 6. Add a title to the plot in French that translates to evolution of gains according to episodes. 7. Display a grid on the plot for better readability. The purpose of this code is to visually depict the change in total profits over episodes and provide insights into the performance. Visualizations like this can aid in analyzing trends, identifying patterns, and making informed decisions based on the data. It is essential to visualize data when understanding, communicating, or analyzing trends or patterns effectively. The agent class represents an agent for a reinforcement learning trading algorithm. It initializes various attributes such as state size, action size, model name, etc. It defines a neural network model using Keras sequential API with dense layers and ReLU activation functions. The ACT method implements epsilon-greedy strategy for action selection, while the XP replay method handles experience replay during training. These components are crucial for the algorithm as they govern the agent's behavior, decision-making, and learning process. The neural network predicts actions, experience replay stabilizes training, and epsilon-greedy strategy balances exploration and exploitation. This text describes the process of conducting a quantitative analysis of stock prices using the QFIT algorithm. The steps involved are: 1. Setting the stock name as _GSPC_2011 feet, likely representing stock data for the S&P 500 index in 2011. 2. Specifying a window size of 10 and episode count of 50 for the QFIT algorithm. 3. Executing the QFIT function with the specified parameters to calculate the total profits generated by the algorithm. The QFIT algorithm is a custom algorithm for analyzing stock price data and making trading decisions based on historical stock performance. This code allows for performance analysis of a particular stock over a defined period and evaluates the profitability of the QFIT algorithm's trading strategy. Using this code can provide insights into stock market trends, historical performance, and assist in making informed trading decisions based on quantitative analysis rather than subjective judgment or guesswork. This text explains the process of creating a line plot using the matplotlib library to visualize total profits over a set number of episodes. The steps involved in achieving this are: 1. Creating a new figure with dimensions of 15 units in width and 5 units in height. 2. Plotting the total profits data as a line plot on the graph. 3. Adding a horizontal line to the plot at the mean value of the total profits data, from x equals 0 to the length of total underscore profits. 4. Adding a label, episodes, to the x-axis. 5. Adding a label, gains, to the y-axis. 6. Adding a title, evolution of gains over episodes, to the plot. 7. Adding a grid for better readability. This code is helpful for analyzing the trend of total profits over episodes and comparing it with the mean profit value. It provides insights into the system's performance and behavior under analysis. This text describes a class named agent which embodies an entity capable of decision-making within a specific environment. The primary functionalities of this class are: 1. Initialization. The __init___ method sets up the agent with attributes like state size, evaluation mode status, model name, memory size, inventory, etc. It also initializes parameters such as epsilon, for balancing exploration and exploitation, and gamma, discount factor. 2. Model creation. The _model method constructs a neural network model using Keras, comprising dense layers with ReLU activation functions and a linear output layer. 3. Action selection. The ACT method determines whether to explore, random action, or exploit, choose the best action based on model predictions. 4. Experience replay. The XP replay method, commonly known as experience replay, is a technique used in reinforcement learning with deep Q networks. It involves randomly sampling mini batches from the agent's memory to train the neural network model using past experiences. In essence, this code showcases the implementation of a straightforward deep Q network (DQN) agent that interacts with an environment, learns from experiences, and makes decisions grounded in acquired behaviors. This structure is pivotal in reinforcement learning for efficiently training agents to execute tasks within an environment. This text describes the setup of variables and the invocation of a function called QFIT using those variables as parameters. Here is the breakdown. 1. Stock underscore name is assigned the value $GSPC underscore 2011 feet, likely representing a specific stock. 2. Window underscore size is set to 10, indicating the size of a calculation window. 3. Episode underscore count is set to 50, potentially representing the number of training or testing episodes. 4. The QFIT function is then called with stock underscore name, window underscore size, and episode underscore count as parameters. This function seems to involve Q-Learning or reinforcement learning for stock data analysis. The QFIT function is expected to use these parameters for reinforcement learning on stock market data. The window underscore size likely determines the learning period for model patterns, while episode underscore count specifies the training episodes. This code illustrates a common practice of parameter setup and function invocation for complex calculations or learning tasks in financial or stock market contexts. It emphasizes the importance of structured parameter passing in scenarios involving data analysis, machine learning, or financial modeling. This Python script utilizes the matplotlib library to create a line plot. 1. Setting the figure size to a width of 15 units and height of 5 units where the plot will be displayed. 2. Plotting the values in the list or array total underscore profits on the y-axis against their index on the x-axis. 3. Adding a horizontal line at the mean of the total underscore profits list across the x values from 0 to the list's length. 4. Setting the x-axis label as episodes. 5. Setting the y-axis label as gains. 6. Assigning the plot title as evolution des gains and fonction des episodes. Evolution of gains based on episodes in English. 7. Adding a grid to enhance readability. This code aids in visualizing profit evolution over episodes or time, enabling users to interpret data, identify trends, and patterns. The horizontal line denoting the mean profit facilitates understanding the deviation of individual values from the average. Labels and title offer context, and the grid aligns data points for a more readable plot. To install the yfinance package, you can use pip, a Python package manager. The yfinance package is well known for providing a convenient method to retrieve historical market data from Yahoo Finance. Once installed, you can utilize this package in your Python scripts to acquire stock market data for various purposes like analysis and visualization. The yfinance library in Python enables users to download historical market data from Yahoo Finance. By using yfinance download, users can retrieve historical stock price data for the S&P 500 index in the year 2012. The data is downloaded for the symbol $GSPC, which represents the S&P 500 index, covering the period from January 1, 2012, to December 31, 2012. This functionality proves beneficial as it simplifies the process of fetching historical stock market data for analysis, backtesting trading strategies, or other financial analysis requirements. The data acquired through this method can be utilized for numerous tasks like chart plotting, return calculations, or statistical analysis purposes. The term SP500_2012 inches likely serves as a variable name or function call within a programming context. It suggests a potential connection to the S&P 500 stock market index for the year 2012. However, without the code itself, it is challenging to pinpoint its exact purpose. Typically, such code could be utilized to handle or analyze data concerning the S&P 500 index for 2012. This might involve tasks like fetching historical stock prices, computing returns, conducting analysis, or creating visualizations. Access to this code might be crucial for obtaining specific details associated with the S&P 500 index in 2012, aiding in making informed investment choices, research endeavors, or financial modeling. The S&P 500 index functions as a widely used benchmark for evaluating the general performance of the U.S. stock market, rendering it a valuable asset for investors and finance professionals. This snippet establishes three variables: stock_name, window_size, and model_name. Stock_name is assigned the value $GSPC, commonly used for the S&P 500 index. Window_size is initialized with the integer 10. Model_name is set as the string model_EP50, likely representing a specific model in a modeling task. Furthermore, it declares start and end variables with values, 1 January 2012, and 31 December 2012, respectively. These could be applied to define a time range for analyzing or forecasting the stock market index denoted by stock_name. The purpose of this code is to define key parameters like stock symbol, time window size, model name, start date, and end date for subsequent operations or analyses involving stock data or financial modeling. These variables act as inputs that can be employed in further code or functions to examine historical stock data or construct predictive models. The function getStockData_evaluation retrieves stock data for a specific stock symbol within a given time range. Here is an overview of the process. 1. The function utilizes the yfinance library to fetch stock data based on the provided parameters, stock symbol, start date, end date. Subsequently, it reads data from a CSV file in the data directory corresponding to the stock symbol. 2. The stock data undergoes various calculations, such as determining the logarithmic difference between high and open prices, low and open prices, and close and open prices. 3. Using the calculated values, a new data frame named data is built, containing close price, HO, low, and CO for each data point. This data frame is then returned by the function. 4. The function is employed to obtain stock data for the S&P 500 index (GSPC) in 2012, with the resulting data saved in the variable data. This script is crucial for fetching stock data, conducting calculations based on that data, and organizing it in a structured format, data frame, for further analysis or processing. Utilizing Pandas data frame facilitates convenient manipulation and analysis of stock data within Python. This function evaluates a stock trading strategy using a reinforcement learning agent. Here's an overview of its functionality. 1. Creates an agent with a specified model. 2. Retrieves stock data for a given stock name and time frame. 3. Iterates through the stock data time steps. 4. For each step, constructs a state based on stock data and window size. Uses the agent to decide the action, buy, sell, or hold. Updates the agent's inventory based on the action. Calculates the reward for the action. Updates the total profit based on the reward. Adds the transition tuple, state, action, reward, next_state, done, to the agent's memory. Advances to the next time step. 5. Once all time steps are completed, displays the total profit earned from the trading strategy. This code is crucial for simulating and assessing the performance of a trading strategy trained by a reinforcement learning agent. It enables the evaluation of the strategy's effectiveness in a controlled environment before real-world implementation. The function Q_evaluate is commonly used to assess the performance of a machine learning model in a stock trading context. Here is an overview of each parameter. 1. Stock_name, name of the stock being evaluated. 2. Start date of the evaluation period. 3. End date of the evaluation period. 4. Window_size, size of the window for creating input features. 5. Batch_size, size of data batches for model processing. 6. Model_name, name of the machine learning model used for evaluation. Typically, the function takes historical stock data for a specific stock within the provided start and end dates. It then utilizes the specified model_name to predict future stock prices based on historical data within the window_size. The batch_size parameter aids in efficient data processing during evaluation. The main goal of this function is to analyze the performance and accuracy of the chosen machine learning model in predicting stock prices within the specified timeframe. By evaluating the model's performance with historical data, its ability to generalize to unseen data and suitability for real-world stock trading decisions can be determined.